Can you guys hear me well?
Okay, cool. Okay, um, so let's start our lecture today. So one thing to remind you guys that please, if you want to join the video lecture online, please log in via your NCTU G2 account. Okay. Otherwise, I need to keep accepting your request to to join this video lecture. Okay, this is quite annoying actually. Okay, I have every time I will put this notification in my email, this reminder in my email saying you should log in by using your NCTU G2 account. But every time some students they just don't listen. I don't know why. Okay, please do so. Okay, so last time we mentioned that the main topic of the algorithm that we are introducing in this session is the memory-based method. Okay, it's the memory-based method. Okay, and the main idea of the memory-based method is that you want to use again the training data. Okay, the training data in the prediction time, or we say in the testing time. Okay, so there are two things that we would like to emphasize for memory-based methods. Okay, the first thing is the similarity. Okay, so basically you would like to use so basically the main idea is that I would like to use the relationship. I would like to use the relationship, or we say the similarity, or we say the distance between the training data and my testing data. Okay, I would like to use the similarity between the training data and testing data. Okay, to help the prediction. Okay, so of course, under such consideration, you need to define your metric for measuring the similarity or the distance between the training data and the testing data. Okay, so that is the first thing. Okay, you need to define the a distance metric, or we say a similarity matrix. Okay, the second thing is that we know that in the typical machine learning pipeline, okay, the feature representation of your data is a very important aspect. It's a very important component. Okay, it's a very important component. Okay, so you basically will determine what kind of feature you are going to use based on your application and your data. Okay. So when we have a feature representation, when we have a specific feature representation, and we also have a very specific similarity metric. Okay. Now, and if this similarity metric is the inner product, between two feature vectors, and then this is related to so-called kernel. Okay, so basically the idea of the kernel is to use the inner product for computing the similarity between feature vectors. Okay, so again, you will first project your data, no matter this is from the training or testing. Okay, you project your data onto the feature space, such that you have the feature vectors for all your data points. Okay, no matter they are from the training or testing time, and then you compute the inner product between the feature vectors in order to compute their similarities. Okay, in order to compute their similarities. Okay, so So such idea is the kernel function. It's the kernel function. Okay, and here comes one advanced idea about the kernel function is that sometimes we don't know what is the proper feature mapping for my problem now. Okay, what is the proper feature mapping? Maybe I don't know. Okay, maybe it's pretty hard for me to make a decision at the very beginning, right? Okay, I really don't know what is the proper feature mapping. Okay, but you still want to use the memory-based method. Okay, you still want to use the memory-based method. Okay, basically you still want to use your training data in the prediction time. Okay, and actually this is actually quite common that you just want to use some kernels, okay? Because I know the kernel is to compute the similarity, I would say the inner product between the feature vectors, right? Okay. If I have a way to compute the kernel, right? Then maybe I already then I am satisfied already. Okay, then I'm satisfied already. Maybe I don't really care. I don't really care how to compute exactly the feature mapping. Okay, once I know there is a kernel function, and this kernel function is related to a certain feature presentation. Okay, even I don't know how to compute such feature presentation, but I know how to compute kernel, then perhaps that is already enough. Okay, so here I would like to give you I would like to give you several examples to show you why you can have such shortcuts, why you can have such shortcuts, even you don't know exactly how to compute the feature representation, but if you know how to compute a kernel, and this kernel is related to a specific feature representation, then you are already good to go. Okay, so in the following, I will give you some examples. Okay, so now let's try to imagine that you have a very simple form of the kernel function. Okay, and this kernel function is computed by this way. It's computed by this way. Okay, so you can see this computation is actually quite simple. It's actually quite simple. Okay, okay, so this computation of the kernel function is actually quite simple, right? You have your x and s plot, and please note here, x and s plot. Okay, these the x and s plot are the inputs for my kernel function. So x and s plot are now in their original data space. Okay. Okay. So you can see here, this is actually quite easy, right? Because you have your original x and x plot in the data space, and I simply do the multiplication between my x and s plot and then compute the exponential, right? Quite simple. Okay. Okay, but now let's see how. Let's see what is the corresponding feature map to such a simple kernel function. Okay, the corresponding feature map is actually this way. It's actually computed by this way. Okay. Okay. So you can see this formulation is actually quite complicated. Okay. So x here is your data point in the data space. Okay, and now okay, and is sorry, wait me 1 second.
Cool. Okay. So from which slides that you start to hear no voice? From here? from the from here. Okay. So I will try to restart from here. Sorry for such problem. Okay, I'm sorry. I will start from here. Okay, let's go. Okay, so sorry for this microphone problem. I'm pretty sorry about this. So again, okay. So following this idea, right? Okay, the idea is that once I know how to compute a kernel and I know this kernel is related to a certain feature representation, then it's already good enough to continue. Okay, so now let's try to consider this simple kernel computation. Okay, so this kernel computation is basically try to do the inner product between two data points in the data space. Okay, and then perform the explanation. Okay, but for this simple form of the kernel function, actually it is related to a very complicated feature representation. Okay, so it is related to such a feature representation. Okay, you can see this feature computation is quite complicated, right? This is computed by 1 over square root of r fractional times x to the power of r. Okay, and then this r should goes from 0 to infinity. No, this r should goes from 0 to infinity. Okay, so basically that means you are now trying to map your data from its original data space to a infinite dimensional feature space. Okay, so you can try to imagine that under such feature representation, okay, it is almost impossible for you to follow the original pipeline, right? The original pipeline is that, okay, I first have my data in my data space, and then I compute their feature representation, and then I compute their inner product. Okay, this is almost impossible to achieve so because your feature representation now is in infinite dimensional space. It's now in the infinite dimensional feature space. Okay, and then just not to mention that you need to compute the inner products between two feature vectors of infinite dimensionality, right? So this is quite computational expensive. Okay, this is quite computational expensive. Okay, so but anyway, under such complicated feature representation, and then when you try to use this complicated feature representation to compute the inner products, then you can do the math on your own. When you do the math on your own, you will find out actually it can achieve a very simple form of the kernel function. Okay, the only thing you need to do is to compute the inner product in the original data space. Okay, here is to compute the inner product in the original data space. The inner product on the original data space, and then do the explanation. Okay, so here we come. Here just give you a very great example to see that even a very complicated feature representation, it could be related to a very simple kernel. Okay, so here, if you know how to compute a kernel, because this is very simple, if you know how to compute a kernel and you know that this kernel is related to a specific feature representation, that is already good enough. You don't even need to know how to compute the You don't even need to know how to compute the feature. Okay, once you know that there is a kernel and this kernel is related to a certain feature representation, that is already good enough. Okay, and here just want to give you a additional note that the simplest kernel is the identity mapping. Okay, it's the identity mapping. Okay, and it is called linear kernel. Okay, because the simplest kernel is that you are that you are doing nothing for the feature representation. Okay, so basically your feature space is exactly your data space. So here, right, you are actually doing nothing for the feature, and then of course the resultant kernel is directly to directly have the inner products between your original data representation. Okay, and this is the simplest kernel because you are actually doing nothing for the feature extraction. Okay. 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 So here comes another example. Okay. So now your data space is three-dimensional. So that means you have three-dimensional data points, three-dimensional data points. Okay, you have three-dimensional data points. And now let's try to consider this specific feature representation. Okay, so you can see this feature representation is 10-dimensional. Okay, you can do the math on your own if you want to practice. But if you try to compute the inner products between two feature vectors of 10-dimensional defined in this way, okay, you will end up with a kernel function. Actually, this is quite simple, quite easy to compute. Okay, you simply compute the inner products in the original data space plus 1 and do the square. Okay, and do the square. Okay, so that means even now I try to map my three-dimensional data. Into higher dimensional feature space. So now, for example, here 10-dimensional, but it results as a very simple form to compute a kernel. So in this case, once I know how to compute a kernel, how to compute a simple kernel, and I know this kernel is related to a specific feature representation, then it's already good enough, right? Because later on you will see that actually the only computation you need is the kernel function. Okay, you don't really need to compute the feature representation explicitly. Okay. Okay. So here again, just want to give you another example. Okay. So this is actually a very popular kernel function. This is named as radial basis kernel. Okay, this is a very popular kernel function, and you better remember this one. Okay, later on in different algorithms, you are going to use this kernel very often. Okay, so for example now, so this kernel is computation is in this simple way. Okay, you can see here you have the xi and xj in the data space. You compute their L2 norm. And then you multiply with the minus gamma and then do the explanation. So you see this computation is quite simple. Okay, but we can try to check what is the corresponding feature representations of such simple kernel. Okay, and here I just want to give you a very simple derivation. Okay, so basically you can see this one. This is the kernel function. Right? And we can rewrite it. Into, as I say, this is the L2 node. So basically, this is xi minus xj squared. Okay, and this can be expanded by xi squared plus 2 times xi times plus 2 times xi times xj minus minus 2 times xi times xj and plus xj squared. But you also multiply it with the minus gamma. So this end up with this term on the this end up with this term. So actually, for this term, you can actually expand it by using the power series definition. Using the power series, so it will become this complicated. It will become this complicated. It will become this complicated form. So you can see here you need to do, 1 factorial, 2 factorial, 3 factorial, and so on and so on. So you need to compute a lot of factorial and a lot of power. But you can keep going to rewrite your equation. And then you can find out here, right? You can find out here. This is 1 times 1, and here is this term times this term plus this term times this term. So this is similar to the inner product. So we can find out that given this simple computation for the radial basis kernel function, given this simple kernel function, its corresponding feature representation is actually very complicated. So you can see here, this is also a infinite dimensional feature representation. So even a very simple kernel, it could be related to a very complicated feature representation. It could be related to a very complicated feature representation. So I hope these examples are able to give you a very good intuition behind why we only need to know how to compute the kernel function instead of knowing how to compute the feature representation. So let's go back to what we have mentioned in the previous lecture, right? Previously, we have provided you such example to see where the kernel exists. Right? Last time we mentioned about this problem of linear regression with L2 regularization, right? And at last time we have this analytic form for my A. For my A variable, right? And that time you can see from this analytic form of variable A, we have this grand matrix, right? The grand matrix contains all the inner products between your feature vectors, right? So you can see during the prediction, right? The only thing I need is to compute the inner product between my feature vectors, right? But the inner products between my feature vectors is related to kernel. Right? It's related to kernel. So the only thing I need in the prediction time is to compute the kernel, right? So that motivates us again. Once I know how to compute kernel, right? I don't really need to know how to compute the feature. Once I know how to compute once I know how to compute a kernel, it's already good enough. Okay. Okay. So again, let's check this analytic form for this variable a. Okay, you can see here is defined based on the gram matrix plus lambda times this identity matrix, do the inverse and times t, times this vector t. Okay, so even it seems a little bit complicated to do the matrix inversion, right? You can see here you need to do the matrix inversion in high dimensional space. Okay, in high dimensional space. Okay, but we can directly work on kernels. Usually, for example in this radial basis kernel this is really simple to compute. This is really simple to compute. Okay, and we can avoid introducing the explicit. We can avoid explicit introduction of the feature vector, which allows us implicitly to use the feature space of high, even infinite dimensionality. Okay, so that means okay, that means even you are using a very simple kernel, its corresponding feature representation can be very high or even infinite dimensional. Okay, right? But no, because we are able to use very complicated feature. Okay, and usually the complicated feature will give you, always say the high dimensional feature can give you some benefits. Later on, I will give you a very straightforward idea. Okay, so because we really want to have such benefits of using high dimensional feature space, but sometimes okay, let's try to use another description, another explanation. Okay, so now because I want to use a high dimensional feature space, I want to use a high dimensional feature space because it is usually beneficial. Okay, so now I want to use a high dimensional feature space, but I don't want to, explicitly compute it. Okay, so so under this consideration, you can directly go to kernel. You can directly go to kernel, and you can go to a simple kernel, for example, the radial basis kernel, right? So the computation is pretty simple, right? Okay, and then based on the kernel function, right? Based on the kernel function, you don't really need to compute explicitly the features. Okay, so using the kernel function, and then it will provide me the benefit that it will provide me the benefits of complicated feature. Okay, and I can still use the only thing that I need is to have this kernel computation for my prediction. For example, for your linear regression, right? Okay. 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 So that is why we see there is a very important connection from the kernel to the memory-based methods. Okay, to the memory-based method. Okay, because this kernel function is about the is about the computation of similarity between the feature vectors. Okay. 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 So why? Okay. Here, as I mentioned, right, we really want to use the benefits. We really want to have the benefits from high dimensional feature representation, right? Okay. But why? Why do we want to have the high dimensional feature space? Okay. Let's try to consider the least simple case and give you an intuition. Okay. So, for example, now you have these data sets in the you have such data set. This data set is a 2D data set. It's a 2D data set. You have those red dots, and you also have those blue dots. Okay, and now if I want to find out a linear classifier, if I want to find out a linear classifier to separate these two groups, is almost impossible to do so in the original in the original 2D space, right? It's almost impossible, right? How can you find out a linear classifier? So which is a straight straight line. It is impossible to for me to have a straight line, okay, in this 2D space for separating these two groups, right? There's no way to do so, okay. But now, if I try to map it, if I try to map this data set into just a little bit higher dimensional space, for example, 3-dimensional space, okay. If I have a way to map my 2D from my 2D data space into a 3D feature space. So for example, it might end up with these data sets. It might end up with such feature representations. Okay, so now you can see the red dots. Those red dots are mapped into a little bit higher region in this 3D space, and those blue dots are mapped onto a little bit lower region in this 3D space. Okay, and under this feature space, under this 3-dimensional feature space, now this is possible for us to have a linear classifier. Okay, this is now possible for us to have a simple linear classifier, right? I can simply have a linear decision boundary around here to separate the red groups from the blue group, right? Okay, so I hope this can give you a intuition behind why we would like to have a higher dimensional feature space. Okay. So basically, again, we would like to use a higher dimensional, or we say a little bit more complicated feature representation, but it can provide us the benefit that you might be able to use a very simple classifier or a very simple regressor, okay, in that high dimensional feature space. Okay. So again, if you now don't use this high dimensional feature space, that means okay, I now still want to use this 2D. I still want to use 2D as my main representation. Then in this 2D space, if you now want to separate these two groups, if you want to separate these two groups in your original data space, then you need to use a nonlinear classifier, right? You need to use a nonlinear classifier, right? Okay, so that means if you want to use a very simple feature representation, then most of the time, if you want to use a very simple feature representation, then you need to use a complicated classifier. You need to use a complicated model, right? But now, in another way around, if you instead use a higher dimensional feature space. So that means if you are using a more complicated feature representation, then you are able to use a very simple model. Okay, so then basically I think there is a trade-off. There is a trade-off between between your feature representation and also your model. Okay, their complexity. There is a trade-off between the complexity of your feature representation and the complexity of your model, right? But here we just want to motivate you that if you are able to use a more complicated feature, then perhaps you are able to use a very simple model. Okay, a very simple model. Okay, and please know that most of the machine learning algorithm, okay, most of the machine learning algorithms before deep learning, okay, most of the machine learning algorithms before deep learning, they are the main focus of those algorithms is to estimate the model parameters, right? For example, for the classification, I need to model the parameters of my classifier. For regression, I need to estimate the parameters of my regressor, right? Because now the whole the main focus of those algorithms is to estimate the parameters of your model. So now if your model is too complicated, then it is not good, right? If your model is too complicated, then that means it's quite difficult for you to estimate their parameters, right? Okay, so under that consideration, we would like to put most of the complexity onto my feature representations. Okay. So I would like to put most of the complexity to my feature representations, such that I can have the possibility to use a simpler model. Okay. Is this okay for such explanation? I hope it can help you to understand the whole idea. Okay, why we would like to use the high dimensional feature space? Okay, because I want to have the benefit of using simpler model. Okay, in my task or in my problem. Okay. So let's continue. Okay, so you might ask how to construct a valid kernel. Okay, again, we need to know that what is the kernel, right? Again, we need to know the definition of the kernel. The kernel is actually related to the inner product between two feature vectors, right? So a necessary and sufficient condition for the kernel function is that the grand matrix, okay, whose elements are given by the inner product between the feature vectors is positive semi-definite. This is a necessary and sufficient condition for you to define for you to justify if a kernel is valid or not. Okay. And here I just provide you what is so-called a positive semi-definite. But we don't put any we don't want to put any effort to explain that again, because you guys should be familiar with the linear algebra, right? Okay. So basically, if now for a kernel function, okay, if I use a kernel function to compute a grand matrix, if this grand matrix is positive semi-definite, then this kernel is valid. Okay, this is the basic idea. Okay. So this way can help you to justify. This way can help you to justify if your kernel is valid or not. Okay, is valid or not. Okay. And of course, you can try to build kernels from kernels, right? Because as I mentioned, there are some well-known kernels, right? One typical example is this radial basis kernel, and another example is this simplest kernel, okay, so-called linear kernel. So actually, there are some well-known kernel functions. There are some well-known kernel functions. For example, this is also another well-known kernel function, okay. We have, for example, the radial basis kernel, we have the linear kernel, we have the polynomial kernels. You already have some kernels. Those are well known. Okay. So actually, most of the time, people would prefer to build up new kernels from those kernels we have known. Okay. So how can you build up the kernels from kernel, right? So now I want to build up a new kernel function, but I would like to use some kernels I have known as the basic components. Okay, then then here comes some rules for you to use. Here comes some rules for you to use. Okay, for you to combine the kernels into a new kernel, right? So for example, if you have K1, this kernel function, which is what you have known, okay, then you can simply say, okay, I can do a scale. Okay, a scale of a kernel is still a valid kernel. The function of a valid kernel is still a kernel. The exponential of a valid kernel is still a valid kernel. Okay, the summation over kernels is again a valid kernel. Okay, the multiplication, or we say the product between kernel functions, is still the kernel. Okay, so here we just provide you various ways of combining valid kernels into a new kernel function which is still valid. Okay. So up to here, I want to provide you a recap. Okay. The main idea up to here is to introduce the memory-based methods. That means we want to keep our training data points for further use in the prediction. Okay. And for these memory-based methods, you need to have a metric. You need to have a metric to measure the distance or the similarity between the data points in the feature space. Okay, and then if you use the inner product as your distance, or we say the similarity measurement, if you are now using the inner product as your similarity metric, then it will become a kernel. Okay, so actually the scalar product in X, or we say the scalar product related to X, related to your data, will bring you the possibility to have the kernel trick, right? So I hope you still remember this one. This kernel trick, or we say the kernel substitution. Okay, if your data point always appears as scalar product, then it will be actually good for you to try kernel. Okay, this is the kernel trick. Okay, and actually kernel provides you a way to compute the inner product in the feature space. Okay, the simple kernel computation can be related to complicated feature map. Okay, so actually the kernel actually the kernel function itself is more important than the feature map. Okay, for Okay, for the memory based methods, actually kernel function itself is more important than the feature map. Okay, so sometimes you don't even need to know how to compute the feature map. Okay, once I know how to compute a kernel function, it's already good to go. It's already good to go. Okay, and usually we imagine kernel is providing us a way to project the data into much higher dimensional space. Okay, because a very simple kernel computation can be related to a complicated feature map. Okay, and in the end, we also mentioned how you can build out the new kernel function from the existing kernel functions. Okay, so how to build you can easily build up your own kernel function by combining some well-known kernels. Okay. Okay. So now we will continue to introduce two algorithms. Okay, I have mentioned that perhaps the most powerful regressor before deep learning. Okay, the Gaussian process, and also another important algorithm, support vector machine, is perhaps the most powerful classifier before the deep learning. Okay, but now we would like to introduce you first the Gaussian process. It is mostly used for regression problem. Okay, so previously on linear parametric regression, we have such form, right? This is a very simple form for the linear parametric regression problem, right? Okay, you have your feature representation of your input data X, and then you have the parameters of your regressor, okay, and then this is your regression result Y, okay. So of course, we can put a prior distribution of the parameters, right? We can have some prior knowledge. We can put a prior knowledge about the possible parameters for my model, right? So for example, I can put a prior distribution on the parameters of my regressor, right? So for example, I can put a isotropic Gaussian as the prior distribution over my parameters, right? Okay. So when I put a prior distribution over the parameters of my model, then it actually induces a corresponding distribution over functions, right? So for example, here if I put a prior distribution on my parameters, and you can see here the y is related to inner product between my parameters and the feature representations of my data, right? So once you give a prior distribution of your parameters, then of course the resultant y is also a distribution. It's also a distribution, right? But y itself is a function. Y itself as a function. So now you have the distribution over functions. Okay, you have the distribution over functions. I know it might be a little bit hard to understand now, but later on when I give you more explanations, maybe it's easier to understand. Okay. Okay. So now when I put a prior distribution on my model parameters, and then given the training samples x1 to xn, right? Given those training samples, we can get different random variables, right? So for example, if I now have the x1, then I put it into this equation, then I have the phi of x1. I have phi of x1 and its inner product with the w, right? So phi of x1 together with a w which has a prior distribution, then the resultant y is actually a random variable. It's actually a random variable, right? Okay. So the similar story goes for all the data points, right? So for example, now I have a data point x2. I put it into this equation, so I have phi of x2 and its inner product with the W, which has a prior distribution, then it will end up with this Y of x2, which is a random variable, Okay, so when you have a random variable, when you have lots of random variable from all the input data, from all the input samples, okay, then their joint distribution, right? The distribution over y of x1, y of x2 to y of xn, okay? So the joint distribution over those random variables, is also Gaussian, right? Okay, it's actually easy for you to compute, okay, the mean and the covariance of this joint distribution, okay? Okay, so first, to compute the mean of this joint distribution is actually quite easy. It's just to have the expectation over all those random variables, right? To have the expectation over all those random variables. And now because this random variable is related to W transpose times phi of x, right? So actually we can put this expectation into the W, okay? Because the phi actually is given, right? Once you have the x, then the phi of x is actually given. So the expectation can be go into the W, The expectation over W, okay? The expectation over W, because now our W is distributed according to a Gaussian, isotropic Gaussian, so you have a zero mean. So in the end, expectation over W is equal to 0. So overall, the mean function of this joint distribution is also 0. The covariance can be computed similarly. You can follow this math on your own. So you can see here, this is the expectation over Y times Y transpose. Okay, and then because the phi, this is the feature representation of your input of your training samples. We can leave it out from the expectation. So you have this phi, capital Phi times expectation over W times W transpose times phi transpose. Okay, and this one, the expectation over W times W transpose is actually can be told from here, because my W is distributed following this. So actually, the expectation over W times W transpose is related to 1 over alpha. Okay, 1 over alpha. Okay, so you can see here. Again. You see phi, capital Phi times capital Phi transpose. So this is related to kernel again. Okay. Okay, so here I just want to give you an example. So even you start from a linear parametric regression, so once you put a prior distribution, over your parameters, then those y's will become random variables, and then you can try to compute the joint distribution over those y random variables. Okay. So now we are going to. Okay. Well, before we going to introduce the Gaussian process, okay, I would like to give you a high-level motivation. Or we say the high-level intuition. Okay, so you can try to see here. Okay, this is a very simple regression form. Okay, you can see that what you do in this simple regression problem is that you first try to map your data into the feature space. Okay, you first try to map your data into feature space. Okay, and then you try to have the inner product with the parameter w, right? Such that it can be mapped to the y. Okay, it can be mapped into the y. Okay, so basically that means the relation between the feature vector and y is described by this parameter w, right? Okay. Okay. And now let's try to understand. Let's try to consider the idea from the memory-based methods. Okay. Okay, so if we try to consider the idea of the memory-based method, right? Then the intuition behind is that if, for example, now you have two data points, x1 and x2, if x1 and x2 they are close to each other, then ideally their corresponding y should be also close to each other. Okay, that is the idea, right? So again, if you now have a x1 from the training data, and you have x2 from the test data, right? Then if now I follow the same idea, if x1 and x2 they are close to each other, then their y should be also close. So my prediction of y for this test data point x2, it should be somehow similar to the y1 related to x1 in my training data. Okay, it's okay. So that means now, okay, that means now we try to use the relationship between the data points. Now we try to use the, okay?
Teacher.
Okay.
Sorry, can you use pointer?
Okay. Now we try to. Okay, so later I will show you the cursor. Okay, sorry. Okay. Okay, so because now I just want to give you a very high level idea. Okay. So because now again, intuition behind is that if I have two data points x and s1, they are close to each other, then I would expect their y are also close to each other. Okay, so that means now I try to use the relationship. I'm trying to use the relationship between the data points to define my regression function. Right? Okay, it's okay. So now the whole regression problem will turn into using the relationship between my data points, right? Because I know that if I have two data points, they are close to each other, then their regression results should be also close to each other, right? Okay, so my regressor now can be defined based on the relationship between the data points. It's okay? It's okay? So now we are going, so if you have such intuition, if you just always keep this intuition in mind, okay, it can definitely help you to understand the idea of the Gaussian process. Okay. Okay, so once you have this intuition behind, okay, then it's actually quite easy for you to understand the Gaussian process. Okay. Okay, again, now we try to use the relationship between the data points to define our regressor function, to define our regression function. Okay, if x if you have two data points X, no matter they are from the training or testing, if you have two data point X, if they are closer to each other, then I hope their Y should be also close to each other. Okay? Okay. So now we are going to introduce the Gaussian process, which doesn't use the parametric model, but instead define a prior probability distribution over functions directly. And I know you guys might not be able to understand this sentence now. So let's try to go into the details, and then you can understand that, okay, in a better way. Okay, in a better way. Okay. So let's first try to talk about the definition of the Gaussian process. Okay. So for any set S, a Gaussian process on this set S is a set of random variables. Okay, the random variables is defined based on X. Okay, f of X. Okay, a Gaussian process on this set is a group of random variables. So for any subset of those random variables is distributed according to a Gaussian. Okay, it's distributed according to a Gaussian. Okay. So first, the number of elements in this set S can be infinite many. Okay. Second, the number of random variables f of X can be also any. Right. So here, the main idea is here. Okay. The joint distribution of a group of random variables. Okay, the joint distribution over a group of random variables is multivariate Gaussian. Okay, it's multivariate Gaussian. Okay. 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 Then. And what does that mean? What does that mean? Okay, so here just give you two examples. Okay, so for example, now I can take x9, x5, x2, x7 from my data set S, and then I use f of x9, f of x5, f of x2, and f of x7 to build up a small group, Then the distribute, because these four are random variables, right? And if I use these four random variables to build up a small group, then the distribution, okay, then the distribution of this small group, okay, is actually distributed according to a Gaussian. Okay, so such that you can compute its mean and covariance function of this Gaussian. Okay, and even you can use any arbitrary combinations of the data points. You can use any combination of you can use any arbitrary combinations of your data points to build up this group, right? For example, I can build up another small group which contains f of x7 and f of x8. Again, this small group is still distributed according to a Gaussian. Okay, so you can compute its mean and covariance function. Okay, so the Gaussian processes are parameterized by a mean and covariance function, right? Okay, because so here, right here you define a Gaussian. Here you also define a Gaussian, right? So any arbitrary combination of random variables will become a Gaussian, right? Then for any combination, you can derive its covariance function, right? And then for the covariance function, okay, it's actually related to the kernel. okay, is actually related to kernel, right? This can be told from this computation, right? So for example, you have two random variables, fn and fm. You try to compute their covariance, right? And it's actually can be computed by this way, okay? Fn minus mu of fn, okay, is in the product with the fn minus mu of fm. Okay, this is the mean actually. Okay, minus mean and to the inner product, Okay, and then you will become if you conduct this equation a bit, you will end up with this. Okay, you can see here is the inner product between fn and fm. So this is somehow similar to the inner product in the feature space, right? In the feature space, if you consider f is a feature representation, okay, right? So the covariance function of a Gaussian process is actually related to kernel, right? Okay. So now, because you can see any possible collection, or we say any possible combination of random variables from training data creates a function. So the Gaussian process is a distribution of functions, right? Because any possible collection will give you a function, okay? And you can have many different collections, and all those collections together, okay, will become a distribution over functions. Will become distribution over functions, right? Okay, and then if now we have this Gaussian process. If now we have this Gaussian process, right? The Gaussian process is based on the collection of random variables, right? Okay, and Gaussian. So first, Gaussian process is related to the collection of random variables, right? And it can be parameterized by the mean function, and most importantly, a covariance function, okay, related to kernel, right? So you can see here it's related to kernel, right? And what is a kernel? Kernel is trying to describe the similarity between your feature vectors, right? Okay, it's trying to describe the similarity between your feature vectors. Okay, so the similarity between your feature vectors is actually related to what? It's actually related to the connections between your x. Okay, it's actually related to the connections between your x. Okay, and again, right? Still remember our intuition, right? You now want to use the connections between your data points in order to define your regressor, right? Because if you have two data points, they are close to each other. If, for example, you have x and x plum, these two data points, they are close to each other, then I expect their y, okay, their y and y plum should be also close to each other, right? Okay. This is why the Gaussian process can be used for regression, right? Because again, the Gaussian process is able to model the similarity between your data points. Okay, because the Gaussian process is covariance function. It's related to kernel, right? It's related to kernel. Okay, so that means the Gaussian process already include the connections between your data points the similarity between your data points into its covariance function, right? Okay, then what I should do is that I should try to use those connections, or we should try to use those similarities between our data points to define our regressor, because we know that if there are two data points and if they are close to each other, then their y should be also close to each other. Okay. So now let's talk about the Gaussian process regression, right? After we have described so many intuitions, then let's try to describe the idea behind the Gaussian process regression. Okay. So try to imagine that you now have a data set x, y. You have so many data points. Okay, this is your training data set, and now I want to use this training data set to learn my regressor. Okay, and actually the regression is not so professional statement. Okay, it can be understood in this way. Okay, given a bunch of training data, okay, I want to learn a regressor such that I can predict a new y for a test input x. Okay, and this is basically the idea behind regression, right? Okay, so first I use a bunch of training data. Okay, I use a bunch of training data to learn or to define my regressor, and then given a new test input x, I want to predict its corresponding y. Okay. So basically, I want to use a function f. Okay, that is able to map my input data x to my output data y. Okay, and now let's try to put this function. Let's try to put a Gaussian process on this function. Okay, and also we put a small noise. Epsilon. Okay, we'll put a small noise epsilon on this equation. Okay, so that means we want to learn a function f with arrow bars. So you have some noise. Okay, from your data. Okay, so basically, because now you have the x and in your training data, you have the x and y, right? And now I would like to use my x and y, this is my training data, to learn a function f. Okay, to learn a function that f that is able to perform the regression. Okay, and the only thing is that I try to add a small noise. Okay, a small noise that can help you to model the uncertainty. This is actually help you to model the uncertainty. Between your regression, between your prediction and the ground truth. Okay, this is just try to model the uncertainty between your regression results and your ground truth. Okay. So again, I would like to emphasize again the very basic ideas. Okay, for you to understand the Gaussian process regression. Okay, it is a memory-based method. So we are trying to use the training data in our prediction. Okay, and basically the prediction is based on the relation between the test input and training data. Okay, this is the very important idea behind the memory-based method, and because the Gaussian process regression is actually belongs to memory-based methods. So that means in the Gaussian process, we are trying to use the relation between the test input, the test data and the training data to do the prediction. Okay, the intuition behind is that if you have two data points, x and s plum. Okay, so for example, x is from training data, x prime is from the test data. But anyway, if x and s plum, if they are close to each other in the feature space, then I would expect their y will be also close. Okay, so this is the intuition behind. This is the intuition behind. Okay. So now another important idea that I want to emphasize is that now the whole regression model is now about the whole regression model now is all about the relation between the data points, right? It's all about the relation between the data points. Okay. Okay. So actually, your regressor is now defined based on the relation between the data points. Okay. Okay. Your regression is now defined based on your data points. So we name this type of regression as non-parametric regression. We name this type of regression as non-parametric because now your regression model is actually based on the relation between the data points. Okay. Okay. So the meaning of non-parametric, the meaning of non-parametric, okay, it doesn't stand for that you don't have any parameters in your model. Okay, it doesn't mean that. Its actual meaning, the actual meaning of non-parametric is that you have the number of parameters grows. You have number of parameters grows with the number of data points. Okay, so so let me try to do this here. Let's try to have this here. Okay, the non-parametric, okay, is not sorry, maybe I should. Okay, it doesn't mean that you don't have, okay, don't have any parameters in your model. Instead, it means that you the number of parameters grows with the number of data points. Okay, it's too big. Okay. Okay. Yeah. Okay. So the Gaussian process regression is type of is a very typical example for the non-parametric regression. Okay, because now the regression model is defined based on the relation. It's now defined based on the. Sorry, maybe I should put it here. Sorry. Put it here, put it much clearer. Okay, because now your regression model is defined based on the relation between the data points. Okay, so once I have more data points in my training data in my training set, if I have more data points in my training set, then that means you are using more relations. You are using more relations between the data points to define your regression model. Okay, so the number of the number of parameters grows with the number of data points, because if you have more data points in your training data set, then it provides you more information to define your regression. Okay? Okay? So here I just want to give you some, again, give you some intuition, right? So for instance, okay, those blue dots are your training data points. Okay. So if now I provide you such training data points, and then I asked you what is the possible y given this x test, then I might imagine. Sorry, I might imagine. I might imagine that, okay. I might imagine that there could be a curve like this. There might be a curve like this. So given this x test, I would predict. I would expect that the y should be somewhere here. It should be somewhere here, right? Okay. But if I give you another type of another group of the training data point, okay, then given the x test, given the x test at the same position, you will have a totally different y prediction, right? Okay, for our human intuition, right? For our human intuition, right? If you have this group of data points, then given the x test, I will predict y will be here. But if I now give you another group of data points in the training, then the same x test will result in different prediction y. Okay. Okay. So again, this is related to intuition. This is related to intuition that if x and x plot are close to each other, then their y will be also close. Okay. That is related to such intuition, right? Okay. Okay. So again, because this intuition, right? The intuition that if x and x plot are close to each other, then their y will be also close. Okay. So you need to find out. You need to define a metric. Okay. I don't know why this runs away. Give me a second. Okay, good. Okay. So because of this intuition, right? Again, our regression model now is defined based on the relation between the data points. Okay. So you need to define a metric. You need to define a metric to evaluate the similarity of the distance between x. Okay, and this is actually kernel. Okay, this is actually kernel. Okay, because you can use the inner product to compute the similarity in the feature space. So this is related to kernel. Okay, and the Gaussian process is parameterized by a mean function and also a covariance function. The covariance function is actually related to kernel. Okay, and because the random variable yn equal to f of xn, we can compute the similarity between random variables by covariance. Okay. Okay, we can compute the similarity between random variables by covariance. Okay. Okay. So I'm not sure why it says. Give me a second. I should put it upward. Okay. Okay. So, wait. This is annoying. I don't know why it's shifting this way. Let's try to move it a little bit. Okay. Okay. So now you are able to connect all these things together. Right? Okay. The similarity between the random variables can be computed by covariance, and covariance is related to kernel, right? And why do we the kernel actually is related to this intuition, right? If the x and s point are close to each other in feature space, right? So that is if you use the inner product to define your similarity, then it's related to kernel, right? So all these things can now be connected. Okay, all these ideas are now can be connected. Okay, so again, the kernel function determines determines the kernel function that determines k. Okay, the gram matrix should be chosen to express the property. Okay. So basically, your feature. So basically, your kernel function. Okay, I should say so. You should choose a kernel function. You should choose a kernel function. Okay, that is able to satisfy the intuition. Okay, so you should choose a kernel function that is able to satisfy the intuition that for points xn and xm that are similar, for points xn and sm that are similar, their corresponding values y of xn and y of sm will be more strongly correlated than for this similar point. Okay. So basically, you should try to find out an appropriate. You should try to find out an appropriate kernel function such that it is able to satisfy this property given your training data. Okay. So I want to emphasize again. Okay, you have a training data. You have training data, right? And now you need to find out the kernel function. You need to find out the kernel function that is able to satisfy your training data. Okay, and how to satisfy your training data? Okay, basically for the points xn and xm, if they are similar, then their corresponding values yxn and yxm, okay, should be more strongly correlated than for this similar points under your choice of the kernel function. Okay. So now in the Gaussian process regression, the main idea is to find out a proper kernel function such that the connections between x can be nicely mapped to the connections between y. Okay. So here I just want to emphasize again that in this Gaussian process regression, okay, we don't have any parametric form like yx equal to w transpose times phi of x. We don't have such form anymore. We only have this form, yn equal to f of xn. So f is just a function, okay? And the Gaussian process is not parametric because parametric doesn't mean there is no parameters. Instead, it means the number of parameters will grow with number of data. Okay, so this is just what we have mentioned previously. Okay, so let's try to check about this formulation. Let's try to check about this formulation of the Gaussian process regression. Okay. So again, so again here we have yn equal to f of xn plus epsilon n, and epsilon n is a Gaussian distributed noise. So we actually can call it a Gaussian noise, or we say a white noise. Okay. So let's assume you have so many data points x1 to xn, and you can apply the function of it. You can apply the function on that, so you obtain f of x1 to f of xn. Okay, and we noted this group as the capital F, as this f variable. Okay, and we have so many y, the corresponding outputs, okay, y1 to yn, okay? So basically, the P of y given f, the P of y given f is actually follows a Gaussian distribution, okay? It actually follows a Gaussian distribution, okay? Okay, so you can see the variance is related to here. It's related to your Gaussian noise here. Okay, and the P of f is actually the P of f, right? The P of f. This is related to Gaussian process, right? The joint distribution of those random variables f1, f of x1 to f of xn. The joint distribution of these random variables together, it will become still a Gaussian. Right? This is the definition of the Gaussian process, because we say f now should follow Gaussian process. Okay, so it's the joint distribution of these random variables. Okay, is zero mean, and the covariance is a kernel. It's a graph matrix based on kernel. Right? Okay. Then the marginal likelihood, right? The marginal likelihood. So for example, here this is P of f, this is Py given f. So if you multiply them together and integrate over f, then you have P of y. And this is the marginal likelihood. It's actually distributed according to this. Okay? It's distributed according to this. Okay? Where this P of y is still distributed according to Gaussian. Okay, where the covariance matrix C. Okay, where is covariance matrix C has the elements like this. Okay, see, this is the kernel between xm and xn and xn plus the beta. The beta inverse here. Okay, this is related to your this comes from your white noise. Okay, and here this delta nm. Okay, is different. Delta nm is equals to 1 if n equals to m. Okay, so maybe I should put this here. Okay. Delta, wait me a second. Delta, wait, where can I have it? Sorry, I can. Let me just 1 second. Okay. Okay. So delta. Okay, I know how to do it. Okay. Insert question. Okay, delta equal to 1. Okay, if n equal to n. Okay, and 0 equal to 0 otherwise. Okay, so basically delta function here means that if n equal to n, then delta will be 1. Otherwise, it will be equal to 0. Okay. Okay, so you can imagine that you only have the beta inverse on the diagonal of your covariance matrix. Okay. Okay. So this is py. Okay, py is now still distributed according to Gaussian, and its covariance is defined in this way. Okay. Okay. So this is the marginal likelihood. This is the marginal likelihood. The marginal likelihood is distributed according to Gaussian, and its covariance is defined by C. Okay. Okay. Okay, and you can see from this illustration, right? You have so many data points noted by the purple color. Okay, and then the regression. Okay, the regression is basically follow this blue line, and because of the arrow bars, we have those red lines, those red curves. Okay. So if I want to do the prediction, right? Given a test input data x star, okay? Given a test input data x star, I want to do the prediction. Okay? Okay? If I now wanted to do a prediction, okay? Because we know that all the f, okay, all the random variables comes from the training data and testing data together, still would become a Gaussian distribution. Okay, so previously we say here the f here is the joint distribution over all random variables. Here is only based on the training data. But even we add a random variable comes from the test data, altogether is still distributed according to Gaussian. Okay. Okay. So that's all because we know the collection of all the random variables comes from coming from the training and testing data. Okay. Together, it will still be a Gaussian. So if we want to predict the distribution of new f star, okay, so that means we want to do the regression, right? We want to do a regression for x star. We just need to compute the covariance matrix of this new Gaussian distribution, then cut this Gaussian distribution on f star to see the conditional distribution and thus we achieve the prediction. Okay, I know perhaps it's a little bit hard for you to this sentence now, and let's try to check the equation, right? So first we denote this y n plus 1. This new set is equal to y and y star. So this y, the first y is this, right? All the y's in the training data set, okay? And now this y star is the regression results of this test input, okay? But together we name this is y n plus 1, okay? And y star basically equal to f of x star. And x star is a test input, okay? Then we can compute the marginal likelihood of the y n plus 1. Okay, so it's basically still is distributed according to Gaussian, and its covariance. The covariance now is noted by C n plus 1. Its covariance matrix is actually can be written in this way. Okay, C here for this C n plus 1. Its upper right, so its upper left corner is from the original covariance matrix C. Okay, so this size is n by n, capital N. Okay, it's n by n. And here on the upper right corner, you have the kernel between your test input to all the training data points. Okay, so here, see, this is the relation between your test data to all your training data. Okay, on the bottom left corner, you also have this. You also have the same kernel function. It's trying to describe the relation between your test data and your training data, right? Okay, and then you are on the bottom corner. This is the kernel function between x star and x star, and then with the beta inverse because this is on the diagonal. Okay, so given such given such distribution over y and plus 1, then we can compute the conditional distribution. We can try to compute the conditional distribution for the y star for your prediction. Okay, it's actually a Gaussian distribution with the mean function written in this way and the variance function written in this way. Okay, written in this way. Okay, because now you already have, when you have the py n plus 1. So I think here it should be also the py n plus 1. Okay, the py n plus. Sorry. So because you have this marginal likelihood, okay, combining the original training data and the test data, then you can simply compute the conditional distribution. Okay, you can simply compute the conditional distribution, and it can be written in this way. Okay, but anyway, in this prediction, right? So this is the prediction you want to get. Okay, in this prediction, okay, actually you are trying to use the relationship. You are trying to use the relationship between the training data and the test data for you to do the prediction. Okay, so again, you can see this is a memory-based method. Okay, so so I want to summarize just a little bit that in the Gaussian process regression, okay, the most important thing is that you first find out an appropriate kernel function that is able to satisfy your training data, and then in the prediction time, okay, you try to follow this procedure. Okay, first you compute the kernel between your testing data and your training data, and then you compute the conditional in order to get your prediction on your y start. Okay, on your y start. Okay. Okay, so I think we will stop here, and then next time we will continue on how to find out an appropriate Gaussian function that is able to satisfy your training data. Okay, thank you.